Now we come towards the geometrical representation of SHM. We have to remember that when we use this term simple harmonic motion, we are including both periodic as well as oscillatory motion. So a particle is said to be executing SHM if it is moving to and fro about the mean position, and when it is at the mean position, that point is called the node, and the extreme position is supposed to be anti-node. Nodes are the points of minimum displacement and anti-nodes are the points of maximum displacement. Moreover, when harmonic oscillator is reaching to the mean position, we find that at the mean position, its kinetic energy and velocity will be maximum. That is, total potential energy transforms to kinetic energy. But when it goes to extreme position, that is anti-node, we find that displacement is maximum and the whole kinetic energy transforms into potential energy, and velocity at the extreme position, that will be zero, but velocity at the mean position will be maximum. So this is what the main characterization of SHM. And other thing which is important about the SHM is that any particle executing SHM is supposed to be a harmonic oscillator. In case of a harmonic oscillator, when it moves away from the mean position, its displacement goes on increasing, whereas another force comes into action, that is called restoring force, and restoring force will be directed towards the mean position. So in case of a harmonic oscillator, the displacement is away from the mean position and restoring forces towards the mean position. Moreover, the restoring force is due to the elasticity and inertia of the medium. We can't expect a medium without inertia and elasticity. So, restoring force is generated, the moment displacement starts. We find that the direction of displacement and restoring force are opposite. So, they are opposite to each other. Displacement is away from mean position and restoring forces towards the mean position. Moreover, restoring force is directly proportional to displacement. If the displacement is along y-axis, then F will be proportional to y, or F is equal to minus ky. In this equation, a negative sign will be taken, that is indicating the direction of displacement and restoring force are opposite to each other. But as the displacement will increase, the restoring force will also increase. So restoring force is directly proportional to displacement, only directions are opposite. Then force can be replaced by mass and acceleration, and then we can estimate acceleration. So these all concepts we have to go through in SHM. When we use the term geometrical representation, we are referring to conventions. Any particle executing SHM is always indicated in uniform circular motion. Moreover, the distance from center of the reference circle to the circumference is supposed to be the longest displacement or longest distance. This is called amplitude. Another thing which is important about the geometrical representation, that the motion of particle is in uniform circular motion, or the particle is moving in uniform circle. So radius will not change. This radius is called the amplitude. So in a uniform circular motion, when the particle is moving from point x to y, we will take the projection of the particle. Particle will be on the circumference. We draw two projections, one on y-axis and other will be on x-axis. So the projection on x-axis will be the horizontal displacement and the projection on the y-axis will be the vertical displacement. So when we are moving in first quadrant anti-clockwise from x to y, the vertical displacements will increase and the horizontal displacements will decrease. Similarly, when particle comes to the second quadrant, we find that vertical displacements decrease and horizontals increase towards the negative sign. and the displacement is vector, so magnitude is always the modulus of that vector. Now, when the particle comes to the third quadrant, we again find that displacement increases and the horizontal displacement decreases. And in the fourth quadrant, we find that vertical displacement decreases and horizontal displacement increases. So these are some conventions we have to use. So now we come to the main context of the geometrical representation of SHM. If a particle is moving with uniform speed along the circumference of a circle, then the motion of the foot of perpendicular drawn from particle on the diameter of the circle performs SHM. So SHM is nothing, it is the vibration of the particles about the mean position, that is in to and fro direction. Now, in order to have the description, as I have explained earlier, the SHM is always explained in terms of uniform circular motion. And in uniform circular motion, all displacements are taken from the center of the circle, and if the particle or the projections are coming towards the mean position, then it means displacements are decreasing. But if the projections are going away from the mean position, the displacements are increasing. So, in the circular motion, the actual motion of particle on circumference will have two projections in two dimensions, one on y-axis and other on x-axis. If the distance from the center decreases, means that displacement decreases. If the distance from the center increases in particular direction, the displacement is supposed to increase. Now, for the geometrical representation, draw a circle with radius equal to amplitude. This is what I have suggested, that radius of a uniform circle, that is supposed to be the amplitude of SHM. And when we say particle is an SHM, it means that it is a oscillatory or it is harmonic oscillator. Suppose a particle is moving with uniform angular velocity omega on circumference of the circle. The foot of the perpendicular drawn from particle on a horizontal or vertical diameter of circle performs a simple harmonic motion. Position of the foot of perpendicular can be represented on diameter at an instant, and position of particle performing the circular motion can be determined by direction of linear velocity. That is, linear velocity means when particle is moving in circle, at a specific point we draw a tangent, that will be the velocity, and the magnitude of that velocity will be known as speed. Then at another instant of time, the particle moves to another position, its speed will remain the same, radius is not changing, but direction changes, so now the velocity will become v2. So whenever harmonic oscillator is going on moving in a circle, its velocity at different instants will be different, indicated by the direction of tangent, but magnitude, that is the speed, remains constant. Now we can see the figure. In the figure, P is a particle or it is a harmonic oscillator. It is moving anti-clockwise. At t is equal to 0, obviously it was at x, and when t will go on increasing, its motion will be increasing and it comes towards y. So what we find is that at an instant, P is the position of harmonic oscillator. So O and P are joined, and OP line is indicating the amplitude, and particle P has traced the angle theta right from the original point. So what we have done, from P we have drawn two projections, one is Pn, the other is Pm. So these projections, when we draw, ON is supposed to be the horizontal displacement and OM is supposed to be the vertical displacement, and vertical displacement is indicated by y. Line PM and ON are parallel and OP is working like a transform, that is transversal. So angle MPO must be equal to angle NOP, and that is equal to theta. Now we have right angle triangle OMP and the side in front of, that is in front of theta, that is supposed to be perpendicular, and two dotted lines are indicated. One of them is longest and that is supposed to be hypotenuse, and other side is supposed to be base. And from this we can generate the general equation of SHM. So if we take into consideration, that is line OM, that is equal to Y. So Y over OP, that will be equal to sine theta, and theta will be omega t because particle is moving in circle. Now angular displacement is theta from horizontal or vertical diameter is determined by joining the particle's position with the center of circle. From the figure, the projection of particle P on diameter, that is on y-axis, is m, then OM is y, is the displacement of SHM at time t. Omega is given as angle traced per unit time, or theta is equal to omega t. If we see the figure, in that figure triangle OPM, from this triangle, right angle triangle, sine theta can be taken as OM over OP, but OM is equal to vertical displacement and OP is amplitude. So sine theta will be Y over A. Y is equal to A sine theta. So OM over OP is sine theta, so cross multiply, and our result will become A sine theta, or it is A sine omega t. Simple harmonic motion is the projection of uniform circular motion on the diameter of the circle of reference, that is on x-axis or on y-axis.